Okay, so let's start. We are looking at Klein-Gordon equation in the last lecture, and we'll continue looking at that equation. What we saw last time was that there are positive and negative energy solutions, and we give them interpretation as particles and antiparticles. Like positive energy solutions like particle and negative energy solutions like antiparticle. Although when initially the solutions were found, antiparticles were not discovered, but nevertheless people tried to give that interpretation. Although this interpretation was given only after the Dirac equation was interpreted properly. Okay, so what we'll do is today is to couple the Klein-Gordon equation to electromagnetic field. And that coupling, of course, would require us to replace P mu by P mu minus E A mu by C, which is what is called the minimal coupling. This is something we discussed last time. And we also talked about the way A0 couples. It has, in the two component form, it comes with a matrix identity matrix, whereas MC squared comes with sigma 3. But even if A0 comes with identity matrix, it is multiplied by E, and the charge E is opposite for particle and antiparticle, and therefore what you actually find is that the Coulomb potential has opposite correction to energy for positive energy particle versus negative energy particle. Okay, and this is kind of consistent with what you would have expected with charged particles and their antiparticles having opposite charge. Okay, so what we'll do is we'll basically look at this system of Klein-Gordon equation coupled to electromagnetic field, and one of the reasons to do that is because at that time the most important question, which is what I basically call litmus test, was to find out the spectrum of hydrogen atom. Okay, so to understand whether you get the hydrogen atom spectrum right, you need to study Klein-Gordon coupled to electromagnetic field. Now, I had mentioned this earlier that Schrödinger, of course, attempted this problem. In fact, he had written down the same equation. He replaced P mu by minimal coupling, and he attempted to solve this, and he found that his results do not agree with the experimental data. So we'll see exactly what is that. What is this problem? Okay. So let's do that. Okay, so let's consider Klein-Gordon equation, and we replace P mu by P mu minus E by C times A mu. And if you write this in a single component, means that means original form, you just replace P square in the operator form by IH bar del X mu minus E by C A mu squared minus M squared C squared psi equals 0. Okay. Now remember that we want to study this system really. If you want to study hydrogen atom problem, you really want to study the Coulomb potential problem. But when you write down the equation in the covariant form, then of course you have a gauge field with all its components appearing in the equation, namely not only A0, but you also have a vector potential A. And the vector potential is the one which is responsible for generating magnetic field. So if you have purely magnetic field background, then in that case, of course, A0 would be 0 and the vector potential would be non-zero, and your magnetic field would be just the curl of the vector potential. Okay. Of course, you know that the magnetic field would be produced by moving charges, and in that sense, if you are studying a static problem, magnetic field would be a subleading effect. Okay, very good. So what we'll do is we'll go back to this equation, and we have this same object written in the vector form here, and you can expand this. You get P squared C squared plus E squared A squared minus EC times P dot A plus A dot P. Okay. At this point, one could make a choice of making a gate choice to be a Coulomb gate, say, which means the divergence of the vector potential vanishes. And if you do that, then P dot A term can also be written as A dot P, because whenever P acts on A, it would vanish because of the choice of gauge. But when you write down P dot A, you actually mean that P acts on anything on its right. So either it acts on A or it goes out and acts on the wave function on the right. And that term is equivalent to A dot P, and therefore you can write this entire expression as 2 times EC times A dot P. Okay, fine. If you have uniform magnetic field, say in Z direction, then the vector potential which follows from this curl equation, B is equal to curl of A, if B is constant, is some constant vector in Z direction, then you can write down the vector potential A to be B by 2 times minus phi times I hat plus X times J hat. Okay, fine. So if you do that, then you can ask, how does this expression A dot P looks like? Okay, and that is that if we have a constant magnetic field in Z direction, then A dot P takes a form E times C by times B. This factor of 2 gets cancelled here, and then dot product of this with P gives you XPY minus YPX. But XPY minus YPX is actually the Z component of the angular momentum. Okay, so therefore B is already in Z direction, so this expression can, in a covariant form, spatially covariant form, can be written as B dot L. Okay, so the A dot P term actually appears as a B dot L term in the when you try to do this computation. Okay, now of course this expression is something we have used already in the non-relativistic theory, and that coupling is something we called mu dot B coupling, where magnetic moment mu is written as E times L upon 2mc. Okay, and given that this quantity appears with factor 1, implies that this expression would, the particle uh, with this kind of interaction would have gyromagnetic ratio 1. Okay, now this is of course distinct from the gyromagnetic ratio 2, which was seen for electrons. Okay, now of course we know why it is 2, because it is attributed to the spin degrees of freedom for the electron. Okay, so if you work back, kind of use this to interpret G equals 1, you would therefore interpret that the Klein-Gordon particle is actually a particle with no spin degree of freedom. Okay, or it's a spin 0 particle. Okay, fine. So as I said, the magnetic field effect is subleading compared to the electric field. So therefore, when we will study atomic physics, we would mostly concentrate on electric field. So, but it is not to say that like we are not going to look at magnetic field at all, or we are not going to look at L dot B kind of coupling. We will. But when you want to solve the problem, you will do the gradations of the terms in the Lagrangian, and then you decide which term you are going to use first. And that depends upon which set of terms we give dominant contribution in the computation. After having obtained that solution to that problem, hopefully exactly, well, won't happen too often, but like, in some cases it may. If you solve the leading problem exactly, say, then you can try to solve the subleading problems uh, approximately, and try to kind of find out how the other terms which were neglected in the beginning when we did the first computation, how they shift the spectrum with respect to the leading computation. Okay, that is a kind of exercise that we will get into as we start talking about atomic physics. Okay, but right now we are still doing relativistic quantum mechanics, trying to solve the hydrogen atom problem itself. Okay, good. So as I said, we are going to kind of ignore magnetic field. So therefore, we are essentially reduced to the electric field problem, and that is generated by the Coulomb potential due to the nucleus with charge Z times E. And therefore, this Coulomb potential is minus Z times E by R. Okay. So what we are going to do is to plug this back into the equation, and given that this is the only potential that the problem has, and it depends only on the magnitude of R, this is the central potential problem. And since it's a central potential problem, angular momentum is a good quantum number. Angular momentum is conserved in this system. Okay, so besides angular momentum being conserved, this, which is related to the fact that it depends only on the modulus of R and not on vector R, it also tells us that we can decompose the solution, particularly for this type of potential, into into a wave function which depends only on the radial variable, and a wave function which depends only on the angular variables. Okay, so this is what we call separation of variables. And so what we will do is we will use this fact that we would be able to do separation of variables, okay, and put it back into the equation and try to concentrate only on the radial part of the equation. Okay, of course, angular part of the wave function would contribute to the radial part of the radial part of the equation, but that is something we will take into account. Okay, so any questions at this point? Okay, so let's go ahead and substitute this wave function into the original problem. The original problem was written out here, this one. Okay, and in this problem, of course, as I said, we are going to ignore the vector potential piece to start with, and we are just going to look at the Coulomb potential part. Okay, and if you do that, then the angular part of the wave function contributes a term which we refer to as the centrifugal potential, okay, piece. And so this is the radial Laplacian, this is the centrifugal potential piece coming from the angular part of the Laplacian, and this is the piece that comes from the original term that we have written down. E is, because we are looking at stationary states, I H bar del t would just give you E. Okay, and A naught is what we are going to substitute as minus Z E upon R. Okay, so I have not done that here yet, but that is the substitution that we are going to do. Okay, so this is our equation. I just want to compare this equation with the non-relativistic equation that we had studied earlier in, say, quantum mechanics 1 course. And that looks, the radial Laplacian looks, of course, identical. This piece also is the same. Okay, and this piece, okay, is bit modified. Okay, first of all, it is a squared quantity here, and then there is a rest energy piece in addition to whatever the quantities you have here. Okay, in the non-relativistic case. Okay, but if you look at the equation in general has a structure which is similar in relativistic as well as non-relativistic case. Okay, although it is a bit deceptive because I have not written a naught right now, but as soon as I write down a naught to be minus ZE by R, then there is a naught square piece which is contributing to 1 over R squared piece here, because it will be Z squared e to the 4 upon R squared. Okay, and so therefore, although this 1 over R squared piece looks the same as this 1 over R squared piece, the total 1 over R squared piece in the relativistic problem is different from 1 over R squared piece that appears here. Similarly, 1 over R piece that you would get here when you do the expansion is different from the kind of piece that you would get here. Okay, here also you are going to substitute A0 to be minus ZE over R. Okay, but nevertheless, one can do that, and one can check that these two equations are in some sense identical. So these two equations are in some sense identical, except for some modification in the values of some parameters. Okay. Can you hold on for a minute? I have to do something. It has started raining and something I have kept outside. I'm sorry.
Okay. Yeah, it's all right.
Yeah, thanks. Hello. Hi. Sorry for this. Okay. So coming back to our equations. So these two equations mathematically are kind of very similar except for change in parameters. Okay. So we will first list what are the changes, and then we'll ask a question as to how we are going to go about solving these equations. Okay. Now, when you solve the differential equation, then you don't solve differential equation for don't solve it for a very specific parameter. You sometimes just keep the parameters free and try to see if you can solve the differential equation for free parameters. And then if you wish, you could kind of choose specific values to get specific answers. Okay. In other words, what I'm trying to say here is that even if this equation looks different from this equation, general behavior of this differential equation is no different from the non-relativistic differential equation. And therefore, the first guess, which of course happens to be right, is that the solution to the relativistic equation would be the same as the solution to the non-relativistic equation, up to some modifications of the parameters appearing in the solution. Okay. So the solution is the radial part of the equation would have a solution which would look like associated Laguerre functions. Okay, it is precisely what was used in the non-relativistic problem. Okay, they were associated Laguerre functions, and and the solution for the relativistic problem also would be written in terms of the same set of functions. Only difference would be the following: that if you look at terms which are order 1 over r squared in the equation, then those terms in the non-relativistic case were L into L plus 1, but in the relativistic case it is L into L plus 1 minus Z squared upon H bar C whole squared. Okay. 1 over r term is, in the non-relativistic case, was 2m Z squared upon H bar squared, but in the relativistic case it gets replaced by 2e Z squared upon H bar squared C squared. Okay. Now you would see that, like, in the non-relativistic limit, if you substitute E is equal to mc squared, this formula is essentially same. Okay. But here in the relativistic case, what appears is really the total energy and not just the mass. The r to the 0 term is just 2me upon h bar squared, which gets replaced by e squared minus m squared c to the 4 upon h bar squared c squared. Okay. So if you do these modifications and related kind of terms that you modify in the solution, then whatever the associated Laguerre functions that you would get under these class of replacements solve the differential equation that we encounter in the relativistic problem. Okay.
Sir, could you move a couple of slides before
Back.
Come back?
Yeah. Okay. Further back.
We are feeding this wave function into the this Klein-Gordon equation only.
Yes.
Okay, but and how are we, like in the Schrodinger case, we knew how to exactly interpret psi, in the sense that mod psi square gave us the probabilities.
That is right.
So here, are we going to follow the same prescription?
No, we are not going to interpret that as a probability. No, we are going to interpret that as the charge density only. Remember, that is what we did last time.
Yes, exactly. So what are we looking for, like in this case? Like, what are we going to evaluate now?
So we are going to evaluate. We are going to try to find out whether the energy spectrum of hydrogen atom comes out right or not. Okay. So that is
Okay.
one physical observable, and we are just trying to see whether this problem gives us the hydrogen atom spectrum right.
So basically those energy E's,
Yes.
okay, along with the MC square term, or
Yeah.
I
So there's
mean,
a MC squared piece which is sitting around, and then
yes,
since we are trying to solve a bound state problem, the total energy is less than MC squared. Okay.
yes, yeah,
So and we are trying to see whether that piece, which is MC squared minus something, whether that piece gives us the correct spectrum or not. Okay, that is the exercise.
all right.
Okay, so we will see that it will actually give you a correct answer, but to the leading order, the problem that we solve in, say, quantum mechanics 1, that answer comes out right. The correction to that is the place where the problem is. Okay, and that's why Schrodinger actually abandoned it. We'll see in today's class only. Okay. Okay, so what we have, as I said, we are going to modify the parameters in this fashion in the associated Laguerre functions so that it solves the relativistic problem. Okay, so now the associated Laguerre polynomials have an exponential fall off for large R, and their behavior at small r is some kind of polynomial. Okay, so let's assume that it goes to 0, say, as r to the L prime. Okay, then if you use that, then you find that L prime into L prime minus 1 is this quantity. Okay, that is L into L plus 1 minus Z squared. So this quantity. Okay, you get L prime into L prime minus 1 simply because there's a Laplacian, the radial part of the Laplacian acting on it, and it will kind of give you an expression of this kind. Okay, so try solving this. This is just a quadratic equation in L prime, and it has an answer which is half into half plus this expression. Okay, 2L plus 1 squared minus 4Z squared e to the 4 upon h bar squared c squared. Okay, so I just want you to pay attention to this factor, which is e squared upon h bar c. This is what is called the fine structure constant, and this number is known. This number is 1 over 137. Okay, so in this square root, the second term is just z squared times alpha squared. Okay, minus 4 times z squared times alpha squared. Okay, that is the expression. Now, given the fact that L prime contains a square root, it tells us that, of course, there are two solutions. There's a minus sign also, which we of course discard. Okay, because that would give you a non-normalizable solution. Okay, but if you choose this sign, even then we have a problem, because inside the square root we have a minus sign, and because of this minus sign, whenever 4 times z squared e to the 4 or z squared times alpha squared uh, becomes larger than 2l squared, 2l plus 1 squared, then the quantity inside the square root becomes negative, and therefore L prime becomes imaginary. Okay, so this is the problem. You can ask a question, what is the value of z for which such a thing would happen? Okay, you could choose the value of L as small as possible for this to happen for us, and the smallest value of L that you can take is 0. Okay, and if you do that, then you find that if z is greater than 137 by 2, okay, then you kind of hit this problem. Okay, fine. But this is a serious problem, simply because if that happens, then you have L prime imaginary, and that indicates instability of the hydrogen atom problem. Okay, and that is problematic for the following reason, that even at that time we knew several atoms which were stable with Z value greater than 137 over 2. Okay, 137 over 2 is not a big number. It is like 69. Okay, integer part is really 68. Okay, so we know, like, gold has value Z to be 79, and lead has 82, and bismuth has 83. They were all known at that time. Okay, and they are pretty stable. In fact, Marie Curie had found radium, which was like 91 or some such thing, and 90, sorry. and that was the kind of material which was radioactive. But before that, most of the materials were absolutely stable. So clearly, this is posing a problem as to how to kind of reconcile this with the experimental observation that larger Z value atoms were actually stable. Okay, fine. So that is one problem that Klein-Gordon equation already poses, and we won't be able to solve that right now. Okay, fine. So the associated, yes,
Can we not view it as putting a lower limit on L?
lower limit on L. Yeah,
We
I have
have
already
12
put the
plus.
lowest limit. I have put L to be 0. That gives
No,
me this.
I'm saying that for a given value of Z greater than 137 by 2, L equals 0 cannot be a solution to this equation.
You are saying that like that instead of that you would say that like if Z is larger than this, then the smallest value of L that you could have is
Some
maybe
positive
2,
value. Yeah.
maybe 2 or something like that,
Yeah.
right? Well, yeah, so that would have been a possibility, but that's not the way the spectrum is seen, right?
Okay.
So for example, if you look at cesium atom has L is equal to 0 state. Okay. And it is much heavier than 68. So that is the kind of problem that we get into. Okay. Fine. So coming back to the associated Legare functions, they are product of a polynomial and an exponential function. And this is the kind of structure you have whenever the radial quantum number n prime is a non-negative integer. Okay. So this is a condition that we need to impose, and the reason why we need to impose a condition like this is kind of done by thinking of this as a purely mathematical problem and imposing physical boundary conditions on it. What are the physical boundary conditions that we want to put? We want to say that the wave function vanishes at infinity and wave function is well behaved at r equals 0. Okay, it doesn't kind of go to infinity or some such thing. Okay, either it vanishes or it takes finite value. Okay, so what we do is we substitute r, the radial part of the wave function, to be 1 over r times ur, which is some function which is kind of a polynomial. I'll tell you what is the form that we are going to use, times exponential of some other function of r. Okay, and we will fix these two functions by solving the differential equation in two different limits. Okay, so as we did this in the non-relativistic case, as r goes to infinity limit is taken, then in that limit, whatever differential equation you would get, you will find that f of r is just a linear function of r. It is minus alpha b times r. Okay, where alpha b is the Bohr radius. Okay, so that fixes the exponential function. It is just exponential of minus alpha b r. Okay, as r goes to 0, in that limit you require substituting some kind of a Frobenius series solution, and that is a function of this kind. U of r is equal to r to the sum L prime times a sum over k, a k r
Sir,
to the k. Yes.
this
Yes.
FR should be R over the Bohr radius, right?
Oh yeah. Okay. Sorry, alpha b is kind of inverse Bohr radius. Okay. Thank you.
Yeah.
I'll correct it. Yeah. Of course, it has to be dimensionless quantity. So
Yes.
yeah. Thanks for pointing out my stupid error. Okay. Fine. So I'll just write. I'll correct this thing. I'll just say that it is alpha b is inverse Bohr radius. I think that is easier for me to correct than go down with other corrections with it. Okay. Thank you. Fine. So at r equals 0, we have to substitute a solution of this kind. Okay. And this is something that you do by just studying the behavior of the differential equation around r equals 0, and that would tell you that this is the kind of solution that you would want to substitute. Okay. Now if you try to substitute something like this, then typically every value of ak is non-zero. Okay. So There is no truncation of that. If there is no truncation, then what happens is that when you substitute this into the differential equation, what you'll find that you find a recursion relation which relates ak to ak minus 1 and ak minus 2 and stuff like that, and you can determine ak by knowing the lower values of ak. So you can determine a2 by knowing a0, a1, and then a3 from a1, a2, and so on. Okay. Now, if you determine all AKs and try to plug it back in, then you get the second solution that you would have obtained at r equals infinity. Okay, since it's a second order differential equation, you would have had a plus minus solution here. And this series actually grows as e to the 2 times alpha b r. Okay, and because it is e to the 2 times alpha b r, then that times e to the minus alpha b r would give you the growing solution. Okay, now of course that is not what we want, and to avoid that, what we need to do is to say that this series actually terminates. Okay, so this is something that we do even when we solve harmonic 1D harmonic oscillator problem also, that you say that the series terminate, and the terminating series gives you what are called Hermite polynomials. Okay, so similar thing we'll do here. We demand that the solution should be normalizable. That requires saying that k goes all the way up to only some n prime, okay, which is what we call the radial quantum number. Okay, so here's an exercise. Whatever I said in words now is what you can compute. Take this differential equation, substitute a0 to be minus ze by r, make this answers, and show that fr is this quantity. Okay, after having done that, you substitute u to be this, okay, and demand that the series terminates, that a n prime plus 1 is 0, okay, and using that determine the energy spectrum er for the relativistic problem to be mc squared into 1 plus z squared alpha squared upon nr squared whole to the minus half. That would be the solution. Okay, you can check this. Okay, so it's a straightforward, little longish but straightforward exercise. Okay, and as I said, that since the differential equation is in some sense of similar form as the non-relativistic problem up to shifting parameters, you could just take the non-relativistic problem and shift parameters appropriately to arrive at this answer. Okay, fine. What we will do is we'll use a different method. We will use whatever insight that we developed from non-relativistic problem, and since the differential equation has the same form, we'll use that insight to determine the spectrum of the theory. Okay, so we will do the following thing. As I have emphasized it earlier also, that the differential equation purely mathematically has same form. All that happens is some constants are shifted to some other constants. Okay, so barring that, there is no real change in the equation. So if you put generic values of those parameters, you would be solving the differential equation both for relativistic and non-relativistic problems simultaneously. Okay, fine. Okay, so in a non-relativistic problem, we had learned one important thing, and that is that there is something called a principal quantum number, which is a kind of a sum of the radial quantum number and the angular orbital angular momentum quantum number. That this principal quantum number is related to the coefficients that appear in the differential equation. Okay, so what we will do is we will use that trick to obtain the spectrum. Okay, so the principal quantum number for the relativistic problem, let me call it nr, okay, is, we use the same technique, is half times the ratio of the coefficient of 1 over r term with the coefficient of 1 over r, coefficient of r to the 0 term. Okay, so there are these two coefficients which we had listed. Sorry, we have to go back a little. So there is a coefficient of 1 over r term which is here, and r to the 0 term which is here. Okay, you take a ratio of this divided by this times half. Okay, that was the principal quantum number. What we will do is we will do the same here. We will take this divided by this quantity and take the power half, multiply by half, and write down the expression. Okay, Okay. So in R would take the value, just a sec, I think I have written something. Yeah.
Shouldn't it be
Square
inversely
root.
dependent upon energy?
Yeah, hold on. I have a small error here. I should have written that it's a square root of the coefficient of R naught term, R to the 0 term. Yeah, what were you saying?
I was saying in non-relativistic case, the relation is E is proportional to 1 by n square, right?
Yes. Yes.
So we should obtain that somehow from here also, like somewhat.
Yeah. You will get it. In fact, in the non-relativistic problem, that is how you got it. Okay, so let me just first correct this sentence. Just hold on. Yeah. Okay, so this is how the sentence should really be, that NR is half of the ratio of the coefficient of 1 over R with the square root of the coefficient of R to the 0 term. Yeah. Yeah. So coming back to what you were saying, you wanted 1 over m squared piece, right? Yeah. So you look at the non-relativistic part. Okay. What we are doing is that we are writing this term divided by square root of this term. Okay.
Okay.
And then that quantity involves square root of E. Okay.
Yeah. Okay.
So if you square it, then you get a m squared piece. Okay. Okay. So let's go down. We'll see that also happening. We are going to look at the non-relativistic piece also. Okay. So here's the thing. This is the 1 over R piece, and this is the square root of R to the 0 piece. Okay. Inverted, of course, because it's a ratio. Okay. If you take this is the principal quantum number. Now you invert this entire expression. Okay. When you invert this entire expression, you have to remember one fact, that this quantity is inside the square root is actually negative. Okay. Because of course we have written down modulus here, but total energy is less than m squared mc squared, because you are looking at bound state problem. Okay. So when you use that fact, then you get answer which is ER is equal to mc squared into 1 plus z squared alpha squared upon nr squared to the minus half, which is precisely what the exercise would give you. Okay. This is a straightforward computation by solving the differential equation. Okay. Fine. So this trick basically gives you this answer without solving the differential equation. Okay. Fine. Well, let's compare this with the non-relativistic problem. In the non-relativistic problem, the principal quantum number was the radial quantum number times L plus 1, plus L plus 1. And in that case, you had R to the 1 over R term is here, and R to the 0 term is here, the square root of that, and inverse, of course. You take this, you can write down this expression in this form. Okay. And then you can invert the problem. Okay. So if you invert, you get expression which is like this. Okay. I need not have written down c squared actually. Okay. Fine. So you can obtain the same result by doing the expansion of the relativistic principal quantum number in terms of radial quantum number plus L prime. Okay. Take this expression and you expand that quantity, you get so what you're trying to do is the following, that you take L plus half whole squared outside. Okay. Then you get n prime plus half plus L plus half. Okay. That would give you n prime plus L plus 1. Okay. Which you call n, which is a principal quantum number of the non-relativistic problem. So you take n prime, half, L plus half, all that expression, write that as n. Then you have 1 minus z squared alpha squared divided by L plus half squared, okay, inside the square root. You expand that term, and the first term in the expansion of the square root is this expression, okay, fine. So now you take this expression and put it back into the relativistic problem spectrum, okay, and you will find that you get E is equal to mc squared times this piece plus 3 by 8 times the correction to the bound state spectrum, okay. Now remember that nr itself is related to n by this relation. So we need to, this expression for the relativistic problem is just an expansion of this quantity, okay. You have just expanded this square root in the denominator to write down this piece, okay. But it contains nr, and we need to write down nr in terms of n. So we substitute nr is equal to n minus z squared alpha squared upon 2 times 2l plus 1, and then rewrite the expression, okay. So that gives you, sorry, this should have been just n squared, not nr squared, okay. That gives you an expression which is like this, okay. You can check that this is the non-relativistic hydrogen atom spectrum, okay. If you solve that using the ordinary QM1 problem that we solve, you get that answer, okay. This has the next correction, which is given by this expression, okay, which is 3 by 8 minus n upon 2l plus 1 times z to the 4 e to the 8 upon n to the 4, okay, fine. So we can easily identify these pieces. This is rest energy, this is hydrogen atom spectrum. This is the piece which is called fine structure correction to the relativistic, to the hydrogen, non-relativistic hydrogen problem, okay, fine. Now, of course, we know that the negative sign that appears here is a statement that that it's a bound state spectrum, okay, and we want to understand what is the structure of the of these new corrections, what are called fine structure corrections to the leading order hydrogen atom problem, okay. This expression we have obtained by just expanding the relativistic expression and replacing nr, this is a typo here of course, replacing nr by n, which is the principal quantum number of the non-relativistic problem, okay, fine. So oh, disaster. Yeah. Okay, sorry, I have one more typo, so give me a minute, I'll correct both of them now. That's really bad. Okay. Yeah. So we are looking at the fine structure piece, and Sommerfeld had predicted that the fine structure correction would be something of this type. Okay, 3 by 8 minus n upon 2k times this piece. Okay, so let's kind of go, and k is integer. Okay, that is what Sommerfeld's prediction was, and of course it is important that that we need to look at Sommerfeld's prediction, because this is the factor which agrees with the hydrogen atom spectrum. Okay, the fine structure correction that was kind of measured experimentally agreed with this formula. Okay, let's compare that with Schrodinger's computation, and it is 3 by 8 minus n upon 2l plus 1. Everything else is the same. Okay, it is that you have a odd number sitting in the denominator as against the even number that Sommerfeld had predicted. Okay, and because of this discrepancy, Schrodinger basically abandoned the approach. Okay, and he decided that this way of solving the problem doesn't work, and he decided to take non-relativistic limit of the problem, solve the non-relativistic Schrodinger equation, and got the spectrum including Sommerfeld's correction exactly in this form. Okay, and after having gotten this result in the non-relativistic problem, he was happy that he could get the hydrogen atom spectrum including fine structure corrections correctly, and never visited the relativistic problem again. Okay, fine. So that is the history. Okay, so let's try to understand why there is a discrepancy between Schrodinger's and Sommerfeld's results. Okay, so first thing is that, like, if you are looking at this problem as a problem of electron going around a nucleus, then you need to incorporate the spin of the electron. Okay, so therefore whatever formula Schrodinger has, 2l plus 1 in the denominator, should actually be 2j plus 1, because if you have an electron, then you have not only orbital angular momentum but also spin quantum number, and therefore the correct total angular momentum is j, which is l plus s. Okay, and if you use l plus s as the correct quantum number, then you would find that since l is always integer, okay, and s is half for electron, j would be half odd integer, and therefore 2j plus 1 would have been even integer. Okay, so therefore if he had incorporated the spin of the electron and therefore said that, like, instead of l I should have used j, he would have actually got the right answer in that term. Okay, now this is not to say that it therefore solves the problem. Okay, it is just that if you had incorporated half integral spin for the particle, then it would have given some hope of using an equation of that kind. Yeah, was there a question? Hello?
So from where should we put this, when, like, from the very start?
Sorry?
Like, the mentioning this, that J, instead of feeding in L in the equation, we should have worked with J, you're saying?
Yeah, no, what I'm saying is that, like, Schrodinger used the formula as it is. Okay, if he had said that the particle which is going around the nucleus is a particle with spin half, then he should have actually looked at the total quantum number of that particle, no? Total angular momentum.
I mean, that should come in the differential equation itself.
Exactly,
Then.
exactly. Yeah, but differential equation itself does not contain the spin degree of freedom at all, right?
Yes, so is there something wrong with that only?
Exactly, it is wrong. Yeah, because that differential equation is a differential equation for a scalar particle. In the non-relativistic theory, you introduce the spin degree of freedom by hand.
Exactly,
okay?
yeah.
You just take Schrodinger equation and say, no, Schrodinger equation multiplied by Pauli 2 component column vector. In the relativistic theory, you cannot do this. In the relativistic theory, whatever you write down is a representation of the Lorentz group. If it is a representation of the Lorentz group, which is a column vector, then you use it. If it is not that representation, you cannot use it. Okay, so therefore, in some sense, what Schrodinger did was right, that he did not put a column vector 1 0 or 0 1 and say, okay, I have spin degree of freedom. But what I'm trying to say is that if he is trying to solve, if he was trying to solve the electron problem using the quote-unquote Klein-Gordon equation, then given the fact that the electron has a spin, he should have said that like that angular momentum P should have been total angular momentum. And if he had put that, he would have got the answer right in some sense. Okay, that's what I'm saying. Although although unadulterated calculation would never give you that answer. It will always give you 2L plus 1 there, which is what he got. Okay, is that clear?
Yeah.
Okay. So so one could try to kind of justify a posteriori for a wrong kind of particle anyway, that he could have managed to get even number in the denominator, although the particle actually doesn't carry spin. So there's a issue, and that is why Schrodinger decided to abandon the project. Okay, so we can come back and ask, how did Sommerfeld get the answer right? Okay, so Sommerfeld did two mistakes in some sense. Well, I shouldn't say mistakes, but like he did two approximations, let's call it. He did not consider a spin degree of freedom. Okay, but when he used the semi-classical method for quantization, he also did not use the factor half. Okay, and there is a factor half discrepancy with respect to exact quantization rule, and these two factors of half just cancelled each other, and therefore he got an even number in the denominator. Okay, later on Einstein showed that if you are considering closed orbits, that means orbit which has, if you're trying to solve say radial problem, then the orbit which has two turning points, okay, in that case you need to modify the quantization rule, and you should replace ni's which are integers by ni plus half. Okay, that is what Einstein showed. And the classic example of this half shift is in the 1D harmonic oscillator problem. That one-dimensional harmonic oscillator problem also, there are two turning points. Okay, and the energy spectrum is not integer but integer plus half. Okay, that half shift is precisely what this thing that Einstein showed, that if you are looking at closed orbits in and try to do a semi-classical quantization, then the quantization rule should shift by half. Okay,
so this is the WKB approximation, right?
this is like a yeah, this is a WKB type approximation. Yeah. So but like if you do a semi-classical approximation, you wouldn't see this half coming out very easily. Okay, so that is what Bohr-Sommerfeld quantization is. Okay, so until you kind of look at this WKB type of effect, now Einstein kind of argued it little differently, not following the WKB line, but he basically said that if you have turning points, then you need to do a correction, and kind of provided an argument for why there should be a shift. Okay, but if you do a WKB thing, then you can clearly see this half shift. Okay, without much more, without giving too many physical arguments. Okay, explicit computation shows you that shift. Okay, so coming back to Bohr-Sommerfeld quantization, that is based on the classical action angle variable formulation, and in that what you do is that if you are looking at the period of a canonically conjugate variables, then you would quantize that in the units of Planck constant. Okay, so they said that like if you look at the integral pi dqi, then you say that that should be integer times h. Okay, so this is in some sense what is called is a generalization of what is called the adiabatic invariants of classical mechanics. Adiabatic invariants are the quantities which do not change if you do small modifications of the system. So these are kind of objects which are called piecewise constant, and if you do a large modification, then they can suddenly jump. Okay, so these kind of invariants are the ones which would be physically relevant as Bohr's postulate, and later on Sommerfeld showed that it is not just PDQ only for the linear momenta, but you can generalize it to angular momenta also. That is the Bohr-Sommerfeld formula. Okay, so okay, so Bose-Sommerfeld formula, of course, has the advantage that you can use it only, has the advantage that you can use it when the variables are periodic and when you can do separation of variables. And when you are trying to solve a problem like, say, three-dimensional harmonic oscillator or a hydrogen atom, then they satisfy both these conditions. So therefore, you would expect Bose-Sommerfeld formula to do a good job of describing the system. Okay. So of course, Sommerfeld basically kind of generalized the Bose quantization rule by kind of using the insight from the Kepler problem in classical mechanics, and he said that like the angular momentum also would be quantized. Okay, so that is the additional piece that he introduced, and the radial momentum quantization condition is the one which he proposed, saying that this should determine the spectrum of the theory, and he used that relation to determine the leading behavior of the leading spectrum of the hydrogen atom problem. Okay, so of course quantization tells us that both k and n prime are integers in this case. Okay, yeah, so this is what I just said in fact. Okay, fine. So so any questions here?
Sir,
Yes.
the spin of electron was known at that time.
Spin of electron, when Schrodinger considered the relativistic problem, it was not known. But by the time Klein-Gordon considered the relativistic problem, it was already known. So these, so historically, I mean, like 1924 was Schrodinger's relativistic and non-relativistic attempts. 1925 was Pauli's proposal that it should be, there should be a spin degree of freedom. Klein-Gordon is 1927.
Oh, okay.
So, yeah, so that's how it goes. So, so in fact, Klein-Gordon knew that the particles they are going to look at are not satisfying, do not have any internal degrees of freedom, the kind Pauli had proposed. Okay, so and that is the reason why they knew that, like, they don't expect to get the hydrogen atom spectrum right anyway. So let's study the differential equation, relativistic differential equation anyway. That is how they took the looked at the problem. So they made no attempts of trying to explain any experimental data at that time. That's like doing string theory. No attempts of trying to explain experimental data. Any other question?
What you said that Einstein showed it should be replaced by n plus half. That
Yeah.
is to be done here only.
That is to be done where?
In this
Yeah.
n, like
Yeah.
PDQ.
Yeah.
Something.
PDQI should be n plus half h if you have closed orbits.
Will this work for these elliptical closed orbits in, like in Bohr quantization? It's just nh by 2 pi.
That is right. Yeah.
But that is not correct in the sense that we know that the angular momentum has that under root n, that L plus whatever that.
Yeah. Yeah. But in this particular case, in like WKB formula, for example, is actually n plus half, and it gives you a correct answer. Okay.
It gives you a correct answer for the energies, but not for the angular momentum itself, right?
Yeah. Not for the angular momentum. No, WKB would give you correct answer for even angular momentum actually. WKB would give a right answer for both energy as well as angular momentum. Hello?
Yeah, I'm still wondering, but okay, let's move on.
Okay. Okay. So coming back to this, so let us define the spherical volume element as d omega squared, which is d theta squared plus sine squared theta d phi squared. This is just kind of way you define line element on a sphere. Okay. And we will use this d omega in our calculation. This is kind of following this Kepler kind of line of thinking. So if you look at the kind of classical equations, they would look, the radial part of the equation would look like half m r dot square is equal to the centrifugal piece times the Coulomb piece plus energy. Okay, that is the problem that we had. Okay, so
Sir, isn't an R missing in d omega square?
no. This is for a unit radius sphere. Okay.
Okay.
This defines only the distances on the sphere. It doesn't define the radius of the sphere itself. If you want to define three-dimensional metric, then you would write down dr squared plus r squared d omega squared.
Okay.
Okay. So, but we are looking at only sphere. We are not worrying about what is the size of the sphere. Okay. If you want to worry about what is the size of the sphere, then there should be r squared on both sides. R squared d omega squared will be r squared dr squared plus r squared sine squared theta d phi squared. Okay.
Okay.
Okay. So, so coming back to the radial part of the equation, we look at this equation and we know that we are looking at orbits which are mostly elliptic. Of course, there are some orbits which are circular. For example, if you take k is equal to 0, then that would be a circular orbit. But barring that, most of the orbits are elliptical. And so if you look at the elliptical orbits, then you could ask how r changes as a function of angular variable. So you can write down r dot as dr by d omega times d omega by dt. Okay, fine. But d omega by dt is something we know. Okay, that is the angular momentum, right? That's related to the angular momentum quantity, which is p omega is m r squared omega dot. Okay, and that is quantized. That is some integer L. Okay, which is whatever k times h bar. So this L contains a h bar factor sitting inside it. Okay, um, so you can write down omega dot as L upon mr squared. That is the quantity that I have written out here. Okay, so you can write down r dot is equal to L upon mr squared times dr by d omega. Okay, so you can kind of take this expression and plug it back into this radial part of the equation. Okay, fine. So let's do a little bit of algebra here. When you substitute that expression for r dot, you get half m times L squared upon m squared r to the 4 times dr by d omega squared. That is the left hand side. Right hand side is of course untouched, whatever it was, minus L squared upon 2mr squared plus z squared by r plus e. Okay, so you can kind of massage it a bit. You find that m would cancel. You can multiply by whatever 2m by L squared, and you can kind of simplify this line to write it in this particular form. 1 over r squared dr by d omega times minus, which should be equal to minus 1 over r squared times this expression. Okay, where I just multiplied by 2m by L squared to entire quantity. Okay. Now let's do a change of variables. Instead of using r, let's use rho. Okay, where rho is 1 by r. And the advantage of using rho is that the left hand side becomes simple. Okay, because if you take d rho by d omega, that is same as 1 over r squared dr by d omega. Okay, up to a sign. But since left hand side is squared, that sign is not that important. Okay, so we can write down this term inside the parenthesis just as d omega by d rho. Okay, so therefore d omega by d rho would be a square root of the right hand side. Okay, but on the right hand side you have 1 over r squared, which is same as rho squared. Okay, and then you have a rho here. Okay, because 1 over r piece, and that this piece is as it is. So you get a quantity which is quadratic in rho instead the square root, minus rho squared plus 2mze squared rho by L squared plus 2me by L squared. Okay, this is the kind of expression you get. Okay, so you could ask now that what does what does this give us? Okay. So first thing is that you can just take this and integrate. Okay. So if you integrate this, then you get the answer, which is something like this: omega minus omega naught is equal to sine inverse of rho minus mz square upon L squared divided by this big square root. Okay. Fine. So what we'll do is we'll invert this expression. Okay. So inverting this expression means writing rho in terms of omega. Okay. Since this is sine inverse, it's kind of a simple expression. You write this as rho is equal to this quantity mz is squared by L squared plus square root, which is the denominator quantity, times sine of omega minus omega naught. Okay. So that is the answer. That's how we would solve this equation. Okay. The radial part of the equation in a kind of semi-classical way. Okay. Now you could write down this expression in the following form as 1 plus a times 1 plus epsilon sine omega. Okay, just for convenience, we'll see in a moment as to what is the utility of this. Okay. Fine. So while writing the last one, I just set omega 0 to 0. Otherwise, it was just going out of the screen. Otherwise, nothing very specific about omega equals 0. Omega 0 equals 0. Okay. So fine. So if you do that, then you can kind of read of A to be this quantity mz is squared by L squared. Okay. And epsilon to be square root of 1 plus, so you can kind of check this quantity. There's a common sitting outside. So you can take this factor outside the square root. That is same as mz is squared upon L squared outside. Okay. And then the epsilon is 1 plus inverse of this times this quantity, which is same as 2L squared E upon mz squared e to the 4. Okay. Fine. So now the point is that this expression that we have written down, rho is equal to say a plus b sine omega. Okay. This is an equation of an ellipse. Okay. If this is the kind of dependence rho has on an angular variable, then you would say that this is an equation of an ellipse. Okay. So let's see how that happens. Okay. Fine. So I have already made the claim that this represents an ellipse. So if you have an ellipse with a semi-major axis A, that means the full major axis is 2A and semi-minor axis is B, then you can write down the equation for ellipse in this particular form. Okay, 1 over R is equal to A, which is the semi-major axis, divided by B squared, which is the square of the semi-minor axis, plus square root of A squared minus B squared upon B squared times sine theta, or sine theta minus theta naught. Okay. Now this is pretty much like this expression, because recall that rho is actually 1 over R. Okay. So therefore, if you substitute 1 over R here, then this expression has a form which is very similar, or rather identical, not very similar, but identical to the form that we have used for describing an ellipse. Okay. Fine. Is this okay?
So earlier it should also be minus, right? No?
Which one?
That sign inside the bracket and the under root.
This one?
Yeah, I'm not sure.
Yeah, sine inverse, I think there was a plus minus before the square root.
Yeah. This, because of this one?
Oh, never mind. I think I got it.
Yeah, it doesn't matter, I think. It would give you this answer.
I mean, the eccentricity looks like greater than 1 right now.
Yeah.
Absolutely.
E is negative.
Yeah, E is negative, no?
Oh, okay.
Yeah.
Oh, okay.
Yeah. Okay. Fine. So, so the eccentricity, of course, is related to the major-minor axis ratio in this particular form, that B by A is square root of 1 minus epsilon squared. Okay. And so what we will do is basically we'll identify this factor to be a by b squared, and this factor to be square root of a squared minus b squared upon b squared. Okay, and we can use that set of expressions to which would allow us to kind of write down a to be minus z squared upon 2e and b to be L upon square root of 2me. Okay, fine. And this, if you use, okay, back into this formula for eccentricity, you will find that the epsilon that you get by using a and b in this particular form, that ratio would give you exactly whatever epsilon that we derived here. Okay, so now what we want to do, which I think I kind of finished a bit early today, but what we want to do is to utilize these results to determine the quantization rule and use substitute it in the quantization rule to determine the energy spectrum. Okay, so I think I'll do that in the next class. Okay. Hello?
So these Bohr-Sommerfeld quantization condition, were these given only for bound systems?
Well, they had not given it for the bound systems to start with, but since they wanted to explain the atomic spectra, they always applied it to the bound system. Okay. So, and that is the reason why Einstein's correction becomes important, saying that exact quantization would require that shift. Okay. But Bohr's original postulate was, original proposal was completely a postulate. He just said that like this quantity, if this quantity is an integer, then the charged particle going around another charged particle in an so-called accelerated frame would be stable. Right? That is how it was. Right? Yeah, you're asking something?
Can you go a few slides up where we have the minimal coupling?
Yeah. Oh, beginning of the class.
Yeah, here.
Yeah.
One slide down.
Further up, down. Oh, sorry.
Down.
Yeah.
Yeah. So how can we write the last term like this?
This
two,
one?
where does the 2 comes from? No, the second point.
Oh, this one?
Yeah.
Oh, the thing is that, like, you know, this expression is to be thought of as an operator expression. Okay.
Yeah.
So that means any term that you look at, if it is an operator, it is going to act on anything that is on the right of it. Okay. So now you look at this second expression, and in the second expression, look at only second piece, which is P dot A. Now you write down P as an operator, which is some minus I h bar del del x vector. Okay. That del del x vector dotted with A is equal to 0.
Yeah.
Okay, because of the gate choice. But because it is del del A vector, it may not act on A. It may just go through and act on something on the right hand side. Okay, namely the wave function. Okay, then in that case, this second piece is also A dot P. Okay. And therefore that adds to this to become 2 times A dot P.
Okay.
Okay.
Okay. Yeah.
Any other question?
Sir, in usual like quantum mechanics, whatever wave function we get, we can
Yeah.
also ask questions like something like what is the probability of finding the electron between r equals 0 and r equal to a naught, where a naught is the Bohr radius.
Yes.
Things like that can we ask here?
You cannot actually.
Okay.
You cannot ask that question. So that is a separate problem for the for Klein-Gordon equation. Okay.
So after solving even after solving the partial differential
You would
equation,
have had a probabilistic interpretation would have still had a problem.
yeah. So that wave function is not like useful any more than like what we have already obtained. Like we have independently obtained the energy spectra,
Yes.
angular momentum, and
Yeah.
also what is the maybe M also, the angular that M quantum number.
Magnetic quantum number. Yeah.
Yeah, magnetic.
Yeah. So all those quantum numbers would come out right. In fact, the leading order spectrum also comes out right. It is a subleading order at which you see the error, and but that is the place where you actually see the structure, actually see the spin degree of freedom contributing to physics and so on. Okay. And uh, besides the equation giving trouble in terms of probabilistic interpretation, it is giving trouble even in getting the spectrum right.
Yeah, that is because we are using it for the wrong particle or something.
Oh yeah, absolutely. We are so in fact, like you can try asking a question that like, what if I create an atom where I have a nucleus and a pion is going around it? Okay.
Is that a spin 1 particle?
No, it's a spin 0 particle,
Oh,
which
okay.
is what Klein-Gordon would describe.
Yeah.
Okay. So you and people have studied pion bound state with nucleus. Okay. And I mean, it has a reasonable behavior, but the point is that the spectrum that you see here is not the spectrum which is applicable to that system. Okay, simply because you are looking at a spectrum of a system which is stable. Okay, and pion itself is not stable. So therefore, mm, studying that system of pion kind of forming a bound state with nucleus is a very short-lived thing. It lives for some microsecond or some such thing, and therefore uh, whether it is valid for spin 0 particle going around the nucleus hasn't been tested well enough. Okay, one of the reasons why they wanted to study a problem of this kind was that 137/2 problem. That they wanted to check whether what if they consider heavy nucleus and instead of electrons, if they try to kind of form pion bound states, but it is not even practically possible to do a system like that. So all the experiments trying to have more than 70 pions going around the nucleus have failed so far.
So that 137/2 problem or something like that does not occur in like something like Dirac equation.
No, it doesn't. So we will solve the same problem once again with Dirac equation. So you'll have to bear with me doing the same hydrogen atom problem multiple times. We will do that, and we'll see that it actually doesn't have this 137/2 issue.
Yeah, all right.
Sir,
Yes.
in the last lecture, you mentioned about solving hydrogen problem in parabolic coordinate or something.
Yes. Yeah.
So what is that, and
See,
will we see this later on?
Well, I don't know whether I have it, but like, if you want to see it, I can kind of give that as an exercise. It's a very beautiful exercise. I'll tell you what are the coordinates. And the beautiful part of this parabolic cylinder coordinates is that you need to solve only two equations, really. One is a radial equation, and other one is one of the parabolic coordinate equation. The second parabolic coordinate has the same equation as the rather third one has the same equation as the second one. Okay, so therefore you really need to solve two equations only. In spherical polar, you may think that you have to solve only two equations, but the angular variable actually has two subtle equations sitting inside them. Okay, of course you know that phi dependence is very trivial, but nevertheless it is there. So I will check if I have it in my notes. If I don't have it, then I'll kind of tell you what to do in the and definitely my quantum mechanics notes, quantum mechanics 1 notes, I have done it in parabolic cylinder also. So if you want, I can probably scan and send it.
Yes, sir.
Okay, so at some point I'll probably just put a scan of that in the Dropbox. Okay.
But also, sir, this Kepler problem in classical mechanics, that can also be done in some velocity coordinates. I've heard this. And there the ellipses are circles, something like that.
Yeah, I'm not sure. Maybe, but like, ellipse and circle are not different really. If you can just rescale coordinates, you can make ellipse look like a circle. Okay. So in that case, the eccentricity is the scale relation between two different coordinates. Okay. So mathematically, ellipse and circles are same. In fact, they are all called conics.
Yeah.
So it may be possible, but like I don't know whether in the velocity variables how it will look like.
I thought these two are connected some way, so I just
Possible because okay, I'm not sure.
because I haven't seen the parabolic coordinates. So
No, parabolic coordinates is a different thing. I don't think that is related to this relation.
oh, okay.
Yeah. Any other question?
So for these parts, which book should we follow?
It's the same question actually. See, my problem is that like I have made notes from multiple books, and if you ask me a question from which book, I myself don't remember. In fact, so I will look up and let you know. Actually, is that okay?
Okay.
Because I mean, these are not like I haven't made these notes like recently. They are like 2-3-year-old notes. In fact, 5-year-old notes, I think. So I don't remember. Like I definitely use like 5-6 books. So something from one book, something from another book, and so on. So, but I'll let you know.
Okay.
It will take some time though. Like just trying to spot where it was. Okay.
Okay, it's fine.
Sir?
Yeah.
This minimal coupling approach, is this the first line of attack? Because
no.
we can also think about stronger couplings.
No. In fact, like as you will study in quantum field theory, minimal coupling is the only gauge invariant way of kind of generalizing the coupling of electromagnetism to any charged particle. Okay. So if you want to have a gauge invariant coupling, which also respects space-time symmetries like Poincare invariance, then minimal coupling is probably the only coupling. Of course, you could have higher derivative couplings which are also gauge invariant, but they are not very natural things. There are certain additional effects that one could kind of look at, but I don't think experimentally there is much of a support to that. Okay, but like if you write down a quantum field theory, then there is very little that you can do by means of looking for variations over minimal coupling prescriptions. Okay. So
Okay.
So for example, when you do quantum electrodynamics, which will be part of quantum field theory 1, you will see that you would write down Dirac field coupled to electromagnetic field, and that coupling of Dirac field to electromagnetic field would replace the Dirac kinetic term by the minimal coupling piece. Okay, that is how it will be done.
So pion, you were saying that we can in principle study something like a bound orbit for pion using Klein-Gordon equation.
Yeah.
But like maybe even if we don't have like experimental stuff for evaluating those things or comparing spectra, but
Yes.
other things we can do for pion using Klein-Gordon equation, like scattering or something.
Absolutely. In fact, pion scatterings and all are very well described by Klein-Gordon equation. In fact, the physics of physics of Higgs particle is also completely explained by Klein-Gordon equation. Okay, so it is not the Klein-Gordon equation is not a total dud or something. It is definitely useful, but it is not useful for solving, say, a hydrogen atom problem. Also, it is not useful in a little different way, in the sense that, like, barring the Higgs particle, there is no elementary scalar particle in nature. Until we found the Higgs particle, there was no elementary scalar particle in nature. For example, pion is also a bound state of two quarks. I mean, a bound state of a quark and an antiquark. Okay, so it is not a elementary scalar. It is a bound state of two fermions. Okay, So far we know of only Higgs particle, which is elementary. Okay, until that date, like maybe 2012, 2013 or something, when it was discovered, until that time, there was no known elementary scalar particle for which you could honestly have applied the Klein-Gordon equation. Okay, although all composite scalar particles do obey Klein-Gordon equation, and Klein-Gordon equation or interactions of these composite scalar particles in terms of interacting Klein-Gordon theory is very good fit. It gives you all various results quite I mean in quite good agreement with experiment. Okay, so in that sense, when you elevate Klein-Gordon equation to a Klein-Gordon quantum field theory, that quantum field theory is pretty well behaved actually. Okay, its application to quantum mechanics and relation to atomic spectra was the massive failure of that. Okay, but otherwise it's a well behaved object.
Yeah, all right.
Any other question? Actually, in fact, when you will do quantum field theory, this thing, then most of the techniques that you will develop in quantum field theory course, okay, would be centered around studying interacting Klein-Gordon theory. In fact, so you learn all, well, not all, but like large number of basic quantum field theory techniques using scalar field theory. Okay. Then when you study fermions, when you study gauge fields, then there are additional embellishments that you need to take care of. But basic structure is well explained by scalar field theory, whose free particle or free scalar field equation is the Klein-Gordon equation. Okay.
So also one thing in general,
Yeah.
it is not like as seen by in this problem also, it is not like wise to use an equation for other particles even when spin is not relevant in the problem.
Yeah. It is not actually, because if you have a particle with with spin, okay, whether it is half integral or integral, it satisfies a different equation. So even if its spin degree of freedom is not playing any important role, you may not be able to use Klein-Gordon equation in lieu of that equation.
Yeah, all right.
Yeah. So like for every particle, there's a different equation. Spin half particle has Dirac equation. Spin one particle has something called the Radita-Schwinger equation. No, sorry. Spin three half has a Radita-Schwinger equation. Spin one has some other name. I forget this thing. But like all these equations look different actually. And you cannot replace one by the other, even if you choose to ignore what the spin degrees of freedom are going to do, or whether they are relevant at all. Although like when you will study quantum field theory, you will mostly study spin 0, half and 1. Quantum field theory does not go to 3, half and 2 and stuff like that. 3, half and 2 is something that you will start worrying about only when you do theory of gravity. Supergravity rather, I would say.
And so in principle, we should be able to write an equation for arbitrary spin, right? Like higher also, 4, 5, whatever.
Yeah, in principle, yes. Okay, but in practice, what happens is that like one hasn't found stable particles of that kind. In fact, for a long time, people believed that the upper limit on the spin of the particle is 2. Okay, of course, stable particles. Unstable particles can have like for example, if you look at a nuclei and you ask what is the spin state of the nucleus, you can kind of have very high spin for the nuclei. Okay, but those high spin states of nuclei are not stable states. They would just kind of emit photon and go to the low spin state and so on. But elementary particles with higher spin, one hasn't found them which is higher than, in reality, we haven't found anything which is higher than 1. But since we believe that there is some notion, something called quantum gravity, there will be a spin 2 particle associated with the gravity quantum. which hasn't been found yet, but at least its classical version called gravitational waves have been found a few years ago. This thing. But it is also believed that if you have flat space, then you cannot really have consistent higher spin theories. If you are working in curved spaces, then certain kind of curved spaces can have higher spin theories. But there is a theorem by okay, when I say theorem, I wouldn't remember the name of the guy, unfortunately. But there is a theorem by somebody who shows that, like, if you are studying higher spin theories in flat space, they cannot be consistently constructed as interacting theory. Free theory, of course, you can construct, but free theory is useless, right? Because a free particle doesn't interact with anybody. Okay, so you can always write down a free particle equation, but if you want to write down an interacting theory of higher spin, it is not consistent in higher dimension.
All right.
Yeah, I'm not remembering the name of the person actually. He's a physicist. It's not a mathematician actually, but there's a rigorous statement that in flat space you can't have this. Okay. Any other question?
So was like Dirac lucky when he was writing this his Dirac equation? Because
Actually, not lucky. He was very focused. In fact, we will see that also. That he basically said that, like, what you really want is a first order in time derivative equation. Okay, and the success of Schrodinger equation is in that it is first order derivative in time. So he started off with first order derivative in time, and then he realized that only way he can make sense of an equation of that kind is if he has a matrix equation. Okay. Now, as I said in one of the earlier lectures, that, like, the technique that Dirac uses is what is called Fuchsian differential equation technique, but Dirac doesn't seem to refer to that method at all. So he probably invented it all by himself, actually. So, and then of course his whole purpose of taking the first order time derivative was to avoid negative energy solution that plagued the Klein-Gordon equation. But of course, it was not to happen. He also found negative energy solutions, and then he went through the whatever Dirac sea and holes and antiparticles, and in fact, he predicted the antiparticle of electron to be a proton. Then Pauli had to point out, saying that, like, it has to have same mass. This thing. Then he predicted that it must be positron, and that prediction was proved within 2-3 years. In fact, 1928 and 1931. In fact.
My question was like the Dirac equation is for spin-off fermions. So
Yes.
like and all the experiments, I think all the experiments that were being done during that time would be on electrons. Let's say hydrogen atom or something.
Exactly.
Like
yes. Yeah.
So like that the equation describe electron was something he would not have anticipated.
No, in fact, no, that's not true. In fact, that is what he wanted to do. In fact, his paper says theory of electron. This thing. He's trying to write down a theory for electron. In fact, okay. So, so that is the reason why he knew that he has to have. I mean, like, if you take Schrodinger equation and try to make it in the matrix form, it would be a 2x2 matrix form. Okay. But if you look at the Dirac equation, it is a 4x4 matrix form. And that happens simply because he wants a particle with spin. So he thinks of Schrodinger equation itself as an equation with two components. Okay, the poly column vector multiplying it, and therefore his equation would therefore have twice as much size, and therefore 4 component. So he was trying to get equation for electron.
Okay.
So we will see that as we kind of progress into Dirac equation. It will take some time, but no, it's almost done. I think next lecture will be on that.
Even there, would we face the problem I asked that we cannot ask the question, what is the probability that the electron is between this and this?
No, because it's a first order in time derivative, no? So therefore the rho is psi bar psi. Okay.
Yeah.
And therefore it has a probabilistic interpretation. Okay.
Okay.
Klein-Gordon had a psi bar, sorry, psi star del t psi minus del t psi star psi, and that was a problem in interpretation. But but Dirac equation doesn't have that. It's first order in time derivative, and therefore the charge density or whatever charge in the continuity equation is just psi bar psi. So straightforward probabilistic interpretation.
Okay.
Yeah. Okay. So can we stop here?
Yes, sir.
Okay. Thank you.